Good morning, ladies and gentlemen. May I have your attention, please? Thank you. It's great to see you on this final exams week. Let's go ahead and recall our properties involving logarithms. Today we're going to be using those as we develop a new technique, and that technique is called logarithmic differentiation. It's going to give us a way to handle kind of oddball functions, functions that don't really fit into a particular category for which we already have derivative rules. So we'll be learning a new technique today that will allow us to differentiate those functions, and that's called logarithmic differentiation. But first, go ahead and share with the class how I could rewrite this using properties of logarithms. So how could I rewrite the log of a product, ln of a times b inside? What would that look like? Meg?
ln a plus ln b.
Absolutely. We could write that as a sum of individual logs. Thank you. Raise your hand if you have the same as Meg. ln of a plus ln of b. Keep your hand up if you're willing to share number 2. Go out on a limb there. I know we have some visitors for 1b. Thanks, hands down. Hayden?
ln of a minus ln of b.
ln of a minus ln of b. Raise your hand if you had a difference of individual logs from our 2, a difference. And then our most famous in terms of solving exponential equations and what that does for us, log of a power. How can I rewrite that log of a power? ln of a to the b. Brandon?
That would be b times ln of a.
Absolutely, and that's going to be key, right? Not only when solving exponential equations, but in our logarithmic differentiation process today. So we can bring that exponent, that b, down in front as a multiplier, b times, and then the natural log of the base of the original power. Awesome. Let's go ahead and take a look then at using logarithmic properties to make our calculus lives easier. So let's consider our original expression, y equals natural log of, goodness me, oh my, our original input is a product of powers, and so we've got lots going on there. If we go ahead and rewrite our original using logarithmic properties, we've seen in the past how that makes our subsequent calculus lives much easier, right? If we're going to differentiate that and use calculus to differentiate it, it's going to be much easier. We saw 4 different times if we rewrite our original with log properties. So let's go ahead and do that. What can we do first? Well, in rewriting y, not differentiating, just rewriting our original y, we could go ahead and split that product up inside of my original input as a sum of individual logs, just as we did in applying our property number 1. So we could first rewrite this as ln of x cubed plus ln of sine squared x. After we've split it up as a sum of individual logs, we could go ahead and apply our log of a power property. Property 3, bam, let's bring down those exponents in front as multipliers so that we're dealing with a more simpler natural log function when we finally do get to our differentiation. So again, another rewrite, y equals, not differentiating, just a rewrite. Y equals, let's bring that 3 down in front. So 3 times ln x plus, and again, this is a power. It's just not x cubed, it's sine of x all squared. So I can bring down that exponent in front as well. So 2 ln of sine of x. And now, finally, we're ready for differentiation. So here we go. I know that the derivative of a constant times a function is the constant times the derivative of the function. What's the derivative of ln of x? Jake?
1 over x.
1 over x. Awesome. Thank you. Plus, I know the derivative of a constant times a function is the constant times the derivative of the function. And now we're going to differentiate ln of sine of x. So I'll still use my natural log rules. I know the derivative of the natural log of a function is 1 over the function times the derivative of the function. And my derivative of the function here isn't just x, so the derivative isn't just 1. My input function is sine of x. The derivative of sine of x is cosine of x on top. So let's check to make sure we applied our chain rule appropriately. The derivative of the natural log of the function is 1 over the function times the derivative of the function, and now we're ready to rewrite. So it looks like my final answer, y prime, is given by 3 over x plus 2, and I'm going to go ahead and group this as cotangent of x, and raise your hand if you had the same thing for number 4. So we had the same thing for number 4. Awesome work, you guys. Great. What questions do you guys have about using your log properties to make your calculus lives easier? I think in some ways that's easier to recognize than number 5 and number 6. I saw some people struggling with number 5 and number 6 because we're reframing, right? We're reframing our task from differentiation to integration, and seeing how those different components fit together is key when deciding what overall rule I'm going to utilize to find an antiderivative. So everybody, let's consider number 5, the integral of the natural log of x over x with respect to x. And so we've got some options here. We've got 2 distinct pieces. 3, really, if we think about how we group them. We've got the natural log of x, right? We've got x to the first, but we also have 1 over x. If we think about that x on bottom, right, as x to the negative 1 or 1 over x, the key is deciding, when we have multiple pieces, which is the derivative of which, right? In other words, if there's two distinct components, is one acting as the derivative of the other piece or a portion thereof? And so I want to pose this question. Is natural log of x the derivative of 1 over x? Or is 1 over x the derivative of the natural log of x? Brandon?
Derivative of 1 over ln over x.
Absolutely. That 1 over x, that x on bottom, is there to act as the derivative of that natural log of x, right? Which is a quantity on top to the first power. And so this 1 over x dx, squiggle underline, that 1 over x dx, is there in blue, acting as the derivative of that quantity, natural log of x to the first power. What rule would I use to integrate natural log of x to the first power? So long as I have the derivative of the base present. So I'd use the same rule, right, that I would use to integrate any power function. Right? This is the power rule, so long as I have the derivative of the base. And because I have the derivative of natural log of x present, I can simply integrate by adding 1 to the exponent, right, and dividing by the new exponent. Now, raise your hand if you recognize that. So who got ln squared of x over 2? Ln squared x over 2. So we've got 3, 4 out of 5 out of 24 people. Okay, so that's not so good. We certainly want to improve on that. So how can we make that more accessible? If you didn't recognize that, well, we could choose, right, u to equal that quantity ln of x on top, and then use u substitution as a means for determining the relationship between those pieces and what fits where. That is to say, the derivative of u with respect to x would be given by the derivative of natural log with respect to x. That would be 1 over x. Solving for du to see how my pieces match, I'd multiply that dx to both sides, and I get 1 over x dx. And I'd see that that's exactly what I have squiggle underline, is this 1 over x dx. That's exactly what I have squiggle underline. And so if I were to make a u substitution for this and rewrite my original integral, not with x's, but with u's, I would get u to the first. Plugging in for dx, or 1 over x dx, I put du. And now it's easy to recognize what rule I would use. How would I integrate u with respect to u? Well, I'd add 1 to the exponent and divide by the new exponent. This is equivalent to u squared over 2 plus c, which in turn would equal my original ln of x, quantity squared over 2 plus c, which would equal ln squared x over 2 plus c. Wow! So determining the relationship between the different pieces is of paramount importance when determining what overall rule we're going to pursue when finding an antiderivative, that is, an indefinite interval. All right, back to question 1. Is ln of x the derivative of 1 over x, or is 1 over x the derivative of ln of x? Or is 1 over ln of x the derivative of anything? Right? What's the derivative between the pieces? Or I'm sorry, what's the relationship rather between the different pieces here? Right? What overall rule are we going to use? Then we got it? Anybody recognize this one? Riley?
The natural log overall.
Absolutely. The overall rule we're going to use here to find an antiderivative is the natural log rule. And how do we recognize that? Well, again, the two different pieces, we consider how they're related. In this case, again, 1 over x dx is acting as the derivative of ln of x. It's just that my ln of x quantity is on the bottom to the first power. And what rule will I use when integrating a quantity on the bottom to the first power? Well, because that's a quantity on the bottom to the first power, that opens up the bag for the natural log as a potential rule, right? Remember, we can't use the power rule if I have 1 on the bottom. Right? I'm sorry, a quantity on the bottom to the first power, because that's the negative 1 exponent. When I add 1 to the exponent using the power rule, I get 0, and dividing by the new exponent, I'm trying to divide by 0, and I can't do it. So I can't use the power rule here, but I can certainly use the natural log rule. This would be the natural log of the absolute value of that quantity that was on the bottom to the first power, so long as the derivative of that quantity is present. Is the derivative of ln of x present? Yes, it's that 1 over x dx, just like it was above. So there's no difference between that 1 over x dx and its role in this integration in number 6 versus number 5. It's acting as the derivative of the quantity that I've highlighted in red, ln of x. Awesome. And what do we always need when finding an indefinite integral? A plus c, right? A plus c. So there's my constant of integration. Awesome, awesome. Gosh, I love math. Whew. It's been too long. It's been too long of a break, but today we're going to pull things together and have some more practice, develop a new technique, and within that technique will be lots of opportunities to apply our properties of logarithms in the calculus arena too, so I'm excited about that. What questions do you guys have about your Bellwork? Raise your hand if you didn't get a red mark. So are we good? Awesome. So let's go ahead and take care of our housekeeping. At this time, if you could please take out your OTL number 2. If you have multiple pages, if you could kindly staple them together. There's a stapler on the front desk. You guys need it. There's nothing on the back of the half sheet. So are you guys good? Make sure that your name is on top. Please give yourself credit for those who can take it out of 22, divide it, and multiply by 2. 4 boxes in your mini canvas score nice and big on top. Round to the nearest half point. Final check that your name, right? Your name is on top of your infinite canvas scores box and pass from the back to the front. Thanks, you guys. Thank you. Thank you. Thank you. Everybody good? Great. And I'll try to get these back to you then this hour. Awesome. So, what's new for second semester? Don't worry. It'll still be the same fun-loving atmosphere that seems to say it's okay to enjoy math and have a little fun so long as we get things done. Or we're all about production, baby, but that doesn't mean we can't have a good time. Or I didn't quite catch that subtle reference to the 1990 Super Bowl beer commercial, but it sounded kind of funny, so I'm going to give you the benefit of the doubt this time. But we got new rosters. We'll have new classmates and we'll have new groups, okay? So we'll have new groups for activities starting next class. We're going to be incorporating multiple choice items, right, into not only our assignments, some of our assignments, but into our tests and quizzes. So we'll have some multiple choice items in accordance with the AP exam, where half of your score, right, comes from multiple choice items. So we're going to begin integrating those in some of our exams, our tests and quizzes, which can be good and bad. And then we'll also include some past free response questions that have been released. We'll be including those in some of our tests and quizzes, as well as our homework exercises, as we work towards some AP exam prep. And so, a schedule allowing, it looks like we'll have about a week and a half to devote solely to AP exam preparation, right? We're going to take a full-length timed test in class and use the AP scoring guidelines to get a fake AP exam score. So you can see kind of where you're sitting going into the actual exam. We'll be able to do that in class so that you get a full experience, right? Fully experience not only with the testing but also with the grading and the scoring going into the real exam, so that you can hopefully feel more confident. Okay, so that's where we're headed. What I want to do though is go ahead and share with you your Unit 5 test. And so I'm going to pause the recording now, and when I call your name, if you could come on down. Okay, ladies and gentlemen, so let's go ahead and remind ourselves, right, how our properties of logarithms can help us. We're going to be using these properties of logarithms today as we develop the technique of logarithmic differentiation. So let's go ahead and take a look at old school, right? Old school differentiation. If we wanted to find y prime, the derivative of y, given y as a function log base 6 of x, our old school method would be to rewrite using our definition of logarithms, right? Y equals log base 6 of x if and only if what to the what equals what? Well, y equals log base 6 of x if what to the what equals what? Jake?
6 to the y equals x.
Awesome. So if we go ahead and rewrite the, thank you. If we rewrite that in exponential form, now we'll be ready to differentiate both sides with respect to x. So let's go ahead and differentiate both sides with respect to x. So the derivative of 6 to the y with respect to x is going to require the use of the chain rule. How come? Because this exponential 6 to the y includes an exponent that is itself a function of x. It's not just to the plain Jane x, it's to the y, which is a function of x. And so we'll go ahead and apply the chain rule. I know the derivative of an exponential function is the exponential function itself times the derivative of the exponent. I know the derivative of the exponent is dy dx times the natural log of the base. In this case, the base wasn't e, it was 6, and so that will change the value of my derivative, so times ln of 6. Meanwhile, back at the hacienda, we have the derivative with respect to x of x, and I got the right-hand side. Bam! Right? The derivative with respect to x of x is just 1. Now, what did we want? Well, we wanted y prime. So y prime is my dy dx, and so we isolate y prime, right? That is solve for y prime. We would get dy dx equals 1 over 6 to the y ln 6 if I divided both those things over at the same time. And because my original was y as a function of x, my y prime should be a function of x as well. So let's rewrite without that 6 to the y. But what do we know? Well, we know that 6 to the y is equivalent to x because Jake told us so. So my final answer, y prime, right? If dy dx is y prime, would be given by 1 over x ln 6. That's pretty sweet, but I had to use the chain rule there, right? I had to use the chain rule, and it was much easier, we saw, if we instead rewrote this using our change of base formula, right? Logarithmic properties, right, made the calculus here easier. And so we could rewrite this using change of base, and I thought that was a lot easier. So chain rule was the first way, not chain rule, but change of base will be our second way, and I think that's going to be much easier. Recall that we can rewrite a log of any base b of x as the natural log of input over natural log of base. And so I'll go ahead and again do a rewrite, not calculus, not differentiate, but rewrite log base 6 of x as ln of x over ln of 6 before differentiating to find y prime. So now we can go ahead and treat that ln 6 on the bottom as a constant, right? That 1 over ln 6 is just a constant multiplier, so I'll pull it out in front and simply differentiate the natural log of x with respect to x. I know that to be 1 over x. And voila, it looks like y prime equals 1 over x ln 6. So it looks like y prime equals 1 over x ln 6. Sammy?
Can I ask why the change of base is true? Why we can rewrite this that way?
Yes, absolutely. So let's go ahead and first, Sammy, say, ah, and then say, ooh, and then say, which one was easier? Well, if you remember the change of base, I gotta say that this one was easier. But it doesn't do any good if we don't remember the change of base. So where does the change of base come from? Well, it's back to our definition of natural log. Jake told us that if y equals log base 6 of x, right, then 6 to the y equals x, right? And we want to rewrite this as y equals ln of 6 over, ln of x over ln of 6. How do we get that? Well, let's solve this for y. But now let's solve an exponential for y. All right, how would we solve this for y? Well, my unknown y is not on the ground floor, it's hiding up there in an exponent. So what we need to do to get that variable expression down out of the exponent and on the ground floor where we can deal with it, we'll take the log of both sides. So I'm going to go ahead and take the log of both sides. And we can take any log of both sides. I'm going to take natural log of both sides because in calculus, working with natural log, the derivative of an exponential, right, are easier. So I'm going to go ahead and do the natural log of both sides. So I'm going to take the natural log of 6 to the y is equal to natural log of x, and then you see it already, right? If you grab onto that variable exponent and bring it on top bring it on out of the exponent as a multiplier in front in accordance with the log of a power property, I get y times ln 6 equals ln of x, and solving for y gives me that second line. Voila! Y equals ln x over ln 6. So the change of base is pretty sweet, and we could use any log. We didn't have to use natural log, right? Log base e. We could have used log base 6, log base 4, log base 2, right? But we choose to use natural log 1 because it's on our calculator, and 2 because the calculus of natural logs, right, are so much easier. Awesome. Okay, so that's where we've been, and hopefully with the break I wanted to structure it in and bring you up to speed. Now we're going to go ahead and develop a brand new technique That technique is called logarithmic differentiation. It's going to let us handle a new category of functions, but I don't want to spoil it. And so we're going to go ahead and make sure that you guys get going. We've got some people joining us, and they're just going to integrate into our groups, keeping our maximum group number at 4. So I'm going to have groups of 3 and 4. You can do your usual groups, and then Andrew and Emily, if you see, get in where you fit in. It'll work out great. So we're going to look at activity 6.4. Your stamped eligible items, if you could put a quick circle around, numbers 4, 8, and 10 are stamped eligible items for today's activity. I'm going to go ahead and be around momentarily for questions, but first I'm going to pause the recording, and then we need to resume together for closure at about 11:25. About 11:25, and so that gives us a nice chunk of time. I'm going to pause the recording. So let's go ahead and summarize our steps for applying logarithmic differentiation. If you're anything like me, I did not think that Kathy's method was easier, right? It required on us remembering the definition of inverse properties of natural logarithms and exponential functions of base e. So it was kind of a tricky way, like adding a clever 0 or multiplying by a clever 1, right? But I think that logarithmic differentiation is the way to go, and that was the point of that final question. So what do we need to do for our first step for logarithmic differentiation? What do we do? Bless you. What do we do to both sides as our first step? Emily? Absolutely. So our first step will be take the natural log of both sides. Take the natural log of both sides. After taking the natural log of both sides, we've now introduced our ability to utilize logarithmic properties. So now we'll go ahead and rewrite using our log properties, like log of a power, to bring down that exponent. So we'll rewrite as our second step. And by log properties, we're thinking log of a power, right? That allows us to bring down that exponent as a multiplier in front. And so we could even with that. Next, we'll go ahead and do what to both sides again. So what are we going to do for our third step? Nikki? Good, thank you. For our third step, we'll differentiate both sides. So for our third step, we'll differentiate both sides. And then lastly, we need to then solve for f prime, right, and substitute back in for f of x. And so our final step will solve for y prime. Do you want to call it y prime or f prime? So we'll solve for f prime of x and substitute back in for f of x original. Bless you. Awesome. What questions do you guys have about your 4-step process? Great work. Then I'm going to go ahead and stop the recording now.